This is the last topic of the semester, linear correlation and linear regression. So let's look at these words, linear correlation. We studied correlation, right, in the beginning of the semester. Do you remember? We already talked about this term. What it does is that we are measuring how strong is the relationship or the linear relationship between variables X and Y, for example. What is the correlation between time spent online and GPA? What is the correlation between time spent exercising and body weight, and so on? So basically, we have already established that it's unitless. It ranges between -1 and 1. If it says -1, then it says negative correlation. If it's closer to 1, it's a positive correlation and stronger. So if I were to say a correlation of 0.5 and a correlation of 0.99, I would know that both of these are positive correlations, but obviously the one with 0.99 is a stronger relationship. And if you have a 0, it shows that it's no relation. It shows no relation whatsoever. Do you remember how to measure it? If we want to talk about actual correlation between X and Y, what could we do? There are two things that we can do in the realm of correlation. You could use a scatter plot to get insight. But remember, with a scatter plot, you can't actually know the exact value of correlation. You can only get an idea of how the relation is between X and Y, or you can compute the strength explicitly. So the first one, you could use the scatter plot like this to get insight. You would know that if it's like this one over here, sorry, where's my pointer? If it's something like this, you would know that it's not really a correlation. It's not a linear correlation at all, these two. However, if it goes upward from the left to right, you know that it is strong. It is a positive correlation. Or if it goes the other way around like this, it goes from upper left to bottom right, it is a negative correlation. You also know that if it goes closer to a line, just like these ones on the left-hand side, you know that it is a stronger correlation. But if it's more spread out, like the ones in the middle, it's a little less. The strength is less because it's not a direct linear line. So that is the insight that you can get from the scatter plot. But we also already learned different ways for us to actually compute the actual number of strength. We learned two of these in the beginning of the semester. We had the Pearson R and Spearman rho. Both of them compute the same thing. The only difference is that the Pearson R can be computed with the explicit raw data, but for the Spearman rho, you can also compute it if you have the rank data as well. So after we establish what correlation is, we remember that basically when we have our data and we plot it here on a scatter plot, it can measure the relative strength of the linear relationship between these two variables. Like how strong are they correlated? How are they dependent on each other? And in the context of correlation, the two variables are treated as equal. So I don't care which one occurs first. I don't care if it's X affecting Y or if it's Y affecting X. I don't care if it's GPA affecting time online or time online affecting GPA. However, in linear regression, so previously we had linear correlation. So here in linear regression, we put some weight to these different variables. So instead of assuming that X and Y are equal, we assume that one of them is an independent or a predictor variable. So like the cause and effect. And the other one is the dependent or the outcome of variable Y, or in other words, if I have an X at this value, what happens to my Y? And this would make a Y a function of X. Doesn't that sound familiar? Because here we're trying to model the relationship between X and Y by defining Y as a function of X. Oh, that's our line equation. Y equals mx plus c. Recall, what is c? C is our intersection. What is m? M is our gradient. And that brings us back to your linear equations, your linear equation systems. And you know that for every single pair of variables, you could, in theory, define a linear dependent relationship or a linear regression between x and y. So if you assume that relationship, then this knowledge will give you the ability of inference. So if correlation, it does not fall into inferential statistics. It's just descriptive because it just tells you, oh, the relationship between x and y is this. But here, you're already doing something more. You're doing something to infer something you didn't know before. So if I know x, I can now compute y. Given x, I know y. So if these are the data points that we already know, if I establish the relationship between x and y as a function, so y equals mx plus c, then if I had an x over here, there, for example, this is, I would then be able to determine the value of y. Doesn't that sound familiar? In the context of probability, that is conditional probability. So in other words, linear regression or line modeling that you have already done in linear algebra, in statistics, it is giving you the conditional probability of y given x. So given a value of x, you can compute y, and y given x is then a function of x itself. Here you can use alpha. Previously we used c and m. Here it's just an issue of symbols. So basically you have this linear equation that you can use to model y given x. And you also need to assume that sometimes you have some normal errors, but we're not going to go into the error in this class. So if you have a bunch of data points, you now can assume, you now should be able to determine the line equation, right? You have x, you have y's, now you just need to determine m and c. If you have enough data points, you can make a linear equation system. You can, which you should have already done in your linear algebra course. However, if you recall, some systems are underdetermined, overdetermined, and thus you can use the least squares estimation. I'm not going to repeat that because that should already be covered in your linear algebra course. But in the context of statistics, actually, you can also compute the m and c, or the alpha and beta, whatever symbol you want to use, the intercept and slope, by using your statistical knowledge. You can compute covariance, you can compute variance, you can then compute beta, and then you can compute the intercept. So as an illustration, say I have 3 points of my observation between x and y, that. I show it on a graph on the right. And I ask you, what is this red line? Give me the y equals mx plus c for this red line. You could do a linear algebra solution. As you see here, we have a system, we have a linear equation system here with these two unknowns, a and b, and I have three instances. So I could solve it that way using the least squares formula. Then in my normal system, I can get a solution of a and b, and this is my line equation. Y equals 7 over 2x minus 1 over 2. You can also use a covariance formula. I'm going to leave this on your own. You can try, but theoretically, if you were to compute this using the covariance and variance as well, and this as well, you will end up with the same line equation y equals 7/2x minus half. And lastly, after you have established your line, so after you have all your points, right? You have your points, and then you have your line, your estimated linear regression line. So now if we have our dots and we have our lines, we now can do a residual analysis. So the residual analysis shows the difference between the real data and the estimated one based on your line. So in other words, I want to estimate the error of estimation. I want to plot the estimation, the error of estimation for every dot. So for example here, so for this one, for these set of data, apparently my linear regression, I could have used linear algebra, I could have used the covariance equation. I obtained this line here, okay. So in theory, if I had an X value here, my Y should be on the line, right? But in reality, the data point is up here. So here is a little bit of error. This is our residual. These are my residuals, or these are my errors, you can also say. And if I were to plot the residuals of every single data point, for every single data point, then I would end up with a residual graph like this. So this one would go here and this one would go here. And as you know, there's a difference of shape against the baseline here. And you can see here that that one is not linear and this one is linear, because this one is a curve and this one is rather straight. Aside from linearity, it can also show you about homoscedasticity. Sorry. And what it shows is, so once again, I compute the residuals of this data and the residuals of this data. And since this shape is going outwards like this, it goes that like that. This shows me that there is no constant variance, and this shows me constant variance. There's other things that we can conclude from the residual analysis. If it looks something like this on the left, that it's not independent. If it's like that, it's also not independent. But if it is more or less a straight line like that, then I can say that X and Y are independent from each other. So as a conclusion, the residual analysis from the real data minus the assumed value with the line can show us independence, homoscedasticity, as well as linearity. And that brings us to the end of this material.